is Shahriar. I'm a researcher in CITA, Royal Danish Academy, based in Copenhagen. And today I'm presenting my paper, a workflow integrated adaptive high-resolution, high-quality robotic 3D capture environment called Shiva. For those of you who don't know CITA, CITA is a center for computation in architecture where we do computational design, robotic fabrication, and related fields. This is part of a 5-year EU-funded project called Eco-Metabolistic Architecture led by Mette, Ramsgaard, Thomsen, where we look into actually this butterfly diagram by MacArthur Foundation, as many of you might have seen it, where buildings don't experience a single life arc from design to demolition, but rather multiple successive and even parallel life cycles and cascades. This actually leads to multiple repairs and reuse of the parts, which led to workshops that we had with the students to pick reclaim material of choice and do 3D scanning and some metrology analysis on like load bearing and other things. And I asked them to simply do a 3D scan and overlap them, which was not easily done by the students, but which led to the idea that we should, because there is the idea of auto-alignment of 3D scans since I think 1998, but you don't see any component in Grasshopper or other softwares to do this. So I created this Shiva software. But to begin with, I compared the 3D scan that we had, which is the Zivit, with the photogrammetry, which you can do with your phone, with Femtobolt, which is the Chinese version of Kinect. And as you can see with photogrammetry with Zivit, there is a huge displacement between the two 3D scan, and also the Femtobolt, which is like Kinect, the resolution was lower, which was not enough for our load-bearing tests or other projects that we have, like conformal 3D printing or adaptive 3D printing. So we needed a very fast solution. So in Shiva, which is a Grasshopper plugin, we can do the calibration, auto-alignment of the 3D scans, multi-robot setups, and projection mapping. In the first step, the camera needs to be calibrated. And by calibration, I mean the internal camera calibration, which of course depends on the type of the 3D scanner that you're using. Calibration in here means finding the TCP of the camera relation to the TCP of the robot, because usually robots give you the TCP in their library or SDKs, but we need to have the TCP of the camera relation or transformation matrix to the TCP of the robot. I also have to mention that this is one of the hardest parts that also everyone struggles a bit, because it pretty much depends on the user to do the calibration accurately. But when we get the transformation matrix from the TCP of the robot to the camera, then we have two matrices which can auto-align the 3D scan in this plugin. Some of the other features that this plugin has is that you can track the TCP of the camera and, of course, robot position over time. And then you can repeat the same process if there's some missing 3D scan for some random reason. You can do tracking. In our case, we use biomaterials, and they are highly reactive. So over time, you can repeat your 3D scan in 5 or more days. Or you can do also manual movement with the collaborative robots. And this is an image of the 3D scan that we took. Each color represents a separate 3D scan. And this is a close-up look of how accurate they are. Of course, there are two ways that you can always auto-align 3D scan. One is using the camera position, and the second one is the common feature detection in the point clouds like ICP, iterative closest point. But what was also important in this plugin was to make it as fast as possible. So all of this was, each 3D scan is taken under 1 second, and the auto-alignment as well. But one of the problems we had, as shown in here, is that usually the part is on the table and there's a face missing. So I just thought maybe we can use multiple robots. So using the same technique with all the TCPs from the robots, you can pick the object by one robot and 3D scan using the other robot. So it moves to different positions, and then you can have a 3D scan of the whole part, or you can move to 3 if it's necessary. I don't think it's going to be necessary. So this is the result, as you can see, with the auto-aligned 3D scans. I have to also mention that in this process, it was a bit slower, because if you keep each 2D scan separately, then it needs to follow the robot path. And if you also merge them, so the file actually is bigger, and then it slows down over time. Considering that Zivit 3D scanner and some of the other 3D scanners use structured light, I hacked into the system, and I was able to use it as a projection mapping at the same time. So usually projection mapping is done through a different projector, but because this is a 3D scanner and a projector, you can use it to do a real-time projection mapping, which in this case, for instance, in our biomaterial, we used it to, because they warp, we use it to flatten it and repair it, or inspect our 3D scans on how flat they are. There are not many calibration systems available online to do a projection mapping, and they are mainly manual, and I didn't automate it as well. But you can easily pick the features you want, and then the pictures will be aligned for projection mapping. For future work, we thought that it's possible, of course, using this 3D scanner and projection mapping to do inspection on the reclaimed material, so you can detect the features, or you can of course, overlap thermal cameras or manufacturing processes to the part. So you just put the reclaimed material under the 3D scanning, automatically 3D scans the part. It shows you the manufacturing process that you need to do, and then quickly move forward. And this brings me to the last